start the next unit, maybe for like the first 20 minutes or so, 25 minutes, and then use the second half of class to continue reviewing for your test. So we'll do that every day. Every day we'll cover, go over notes for the next unit, and then continue reviewing for your Friday tests. Oops, sorry, maybe. Okay. But the nice thing here about solving differential equations is that it's process that you already know. You're just having to do problems on both sides of the equation or involve antiderivative process on both sides of the equation, but you already know the procedure. You just have to kind of get used to the process. So it's just so when you go through your calculus step, the rest is just algebra. So hopefully you guys will find these to be familiar in terms of you're just a lot of times doing power rule or use substitution, and then the rest of it is just solving for solving an equation. Yeah, and then Thursday we'll do slope fields, which is not too bad. You just have to get used to that setup. But the second half of class will continue to be review, and then your Friday test will just be 3 FRQs. You'll have a derivative graph, a Riemann sums, and then a particle motion. I'll have help sessions Thursday and Friday morning for a preparation for Friday's test. Okay, so your notes, you guys picked up classroom copies. So I can go ahead and put your notes on a separate sheet if you're using one of my copies. So a differential equation is basically just an equation with derivatives, just a derivative equation. That's all it is. So, but sometimes we have to work on both sides of the equation. So, and we also do an additional step before we can go through our calculus steps. We have to rearrange the equations with our y and dy, which is our anything related to our dependent variable. Usually that's going to be your y variable on the left side, and then your independent variable, that's usually going to be x on the right side of the equation. So for number 1, it says solve the differential equation dy dx equals 2xy over y. Ultimately, this is a derivative equation. We're trying to get it up to the function level. We're going to have to find the antiderivative, but first we have to make sure that all of our pieces are in place. So I like this to be the first step. The first step for me is always cross multiplying. When you cross multiply, it doesn't necessarily get all the variables separated, but it will get your dy and dx's lined up nicely. So I like to always start off with cross multiplying. And the first thing that we would like to do is to make sure that our dx and dy's are in the numerator on separate sides. It's okay to have x's and y's in the denominator, but we definitely don't want our dx or dy's in the denominator. So when I cross multiply, this is what I have. I have 2x dx is equal to, oops, sorry, my bad. I want the y's on the left. So I want the dy's on the left. So y dy is equal to 2x dx. So the first thing that you want to make sure that you have in place is these are your anchor variables. You want your dy on the left and you want your dx on the right, and you want them to be both in the numerator. Okay, so whatever you do when you cross multiply, that's really the whole purpose here. We just want to make sure that these are lined up correctly, and then we can worry about where the other variables go. The y's are already on the left side, so this one is good. Nothing more to do. The x's is already on the right. And then the coefficient can be anywhere, but typically we like to have the coefficient on the right side because eventually it's going to have to end up on the right. And now this is what we call full separation of variables. Anything related to y on the left, anything related to x is on the right. Okay, next up, you're going to now involve the integral because you're still at the derivative level, and your goal is to try to make this equation rise up to the function level. So both sides are just simply power rule process, right? So what does y become? What's the antiderivative of y? Yeah, y squared over 2, just power rule. Technically, there's a plus c, but we're just going to have plus c show up on the right side because a plus c on the left, plus c on the right, if we merge it together, it's still going to be some constant. So we're just always going to force the plus c just to show up once on the right side. Okay. How about the 2x here? What's the antiderivative? Yep. We may have to further do a little bit more work on the left side, but right now I just want to get rid of that denominator 2 there. So we're at the function level. We're just doing a little bit of cleanup. Let me just multiply through by 2. I get y squared is equal to 2x squared. Technically it's 2c, but we know 2c is still a constant. So we'll just do plus c. Eventually, we may have to go a little further and solve for y, but now, I think for now, let's just, technically we've solved the differential equation. We've made our derivative level rise up to the function level. Okay, number 2, solve for dy dx equals x over 1 plus y. Now, the parentheses are there for a reason. If you're solving a differential equation, the parentheses are actually helpful. They're actually there to kind of help you separate the variables easier. So typically we don't want to distribute and get rid of the parentheses. The parentheses are there to kind of help you keep things nicely organized. But my first step is always cross multiplying. So I'm going to force that right side to be a fraction. I'm just going to cross multiply. Again, the whole purpose of cross multiplying is just I want to make sure that my dy and dx's are in their correct spots. That's my first goal. I want my dy in the numerator on the left. I want my dx numerator on the right. Those have to be in place. Okay? We don't ever want dy or dx in the denominator because then our setup is not going to be right. Okay. Any questions so far? So our goal is we want anything related to y's on the left, anything related to x's on the right. What do you see is out of place? Yeah. So the parentheses is helping you organize that expression. So if we want to move the y, the 1 has to go along with it. So we're gonna have to divide that 1 plus y over to the left side. So we're not just going to move the y, we're going to move the whole parentheses. So divide both sides by 1 plus y. It's okay to have x's or y's in the denominator. Okay. It's not okay to have dy or dx's in the denominator. So we're left with dy over 1 plus y is equal to x dx. Okay. This is what we call full separation of variables. We know that algebraically we're set up for our calculus step. Now we're ready to take the antiderivative. Okay, right side is easy. That's just power rule. But the left side requires a little bit of what? Yeah, u substitution. Okay, what's our u value? Yeah, 1 plus y. And this should come out pretty clean. The 1 plus y won't produce anything but 1. It'll just end up being 1 over u du, right? But once you get comfortable, you don't have to go through a full u substitution if you know where it's headed. You can skip that process, especially if you know that your derivative is not going to produce anything except 1. But for now, we'll go through a full u substitution process. But if it was a quiz, you won't have to go through your full, if you go from here directly to find the antiderivative, I'm okay with that. But we know that our dy gets replaced with 1 du. Our 1 plus y gets replaced with u. There's no leftover coefficient. This is cleanly just natural log. So natural log absolute value of u, which cleans up to be natural log absolute value of 1 plus y. So this is the result of that. So if you're comfortable, you can go directly from here to here, and and I would be okay with that because this is manageable. But if you're wanting to go through each of the steps, you're more than welcome to do that as well. Okay, so the left side is done. The right side, x becomes what? Yeah, 1/2 x squared or x squared over 2. And then the plus c is just going to show up one time on the right side. So technically, we've solved the differential equation. We've made everything come up to the function level. The rest is algebra. We're just the last step is trying to solve for y, trying to get that y by itself. So our next step is to find a way to get rid of that natural log. So the way to do that, we're going to raise both sides with e as the base. So exponentiate both sides. So I'm going to raise both sides with e as the base. It'll feel a little messy, but I think in time you're going to see enough of these types of problems where eventually, hopefully, this will get more comfortable. But for now, see if you can follow along. So I'm raising both sides with e as the base. Whatever I do to one side, I can do to the other side. And the benefit here is that we know e and natural log are inverses of each other. So what's going to happen here? Cancel out. So that's nice that we're just left with that abs value of 1 plus y. We're one step closer to solving for y. On the right side here, there's a property. We're going to see. Okay, I'm going to bleed into number 3 a little bit. I want to show this property. The property is that if I have a base raised to the sum of multiple exponents, I can break that up into the product of two bases. So a to the m plus n is same thing as a to the m times a to the n. So the reason that I want to show that is if we can separate this into its individual parts, we can have an easier time kind of seeing what to do with them. So e to the x squared plus c is same thing as e to the x squared over 2 times e to the c. All right, I'm just splitting them up into kind of more separate components. And that plus in the exponent is going to turn into a multiplication at the base level, right? This plus in the exponent turns into a multiplication at the base level. Now, e to the x squared plus c is a variable expression, but what's e to the c? E to the c is just a what? It's a constant, right? So we know a constant can just be represented as just a c. So e to the c is just going to be one large c, right? Because imagine like e to the 5 or e to the 12, that's just going to be some constant. So we're going to convert that e to the c to just be a large times c. So typically we like to have the constant in front. So I'm going to drag that c in front of the e. Okay, and we're still a few steps away, but we're getting closer. We got that right side a little bit cleaned up. We still have to deal with that absolute value. So I'm going to drop the absolute value, but absolute value represents plus or minus. So I'm going to drop the absolute value and bring that plus or minus over to the right side. So 1 plus y is equal to plus or minus c e to the x squared over 2. Now, c is a constant, but the constant can be both positive and negative, right? So basically, the plus or minus can just get absorbed into the c. We don't have to show that plus or minus anymore because the c will just take on both positive and negative values. So I'm going to drop the plus or minus. It's taken care of by the c. And we're almost there. We just subtract 1 over. Now we have y all by itself. All right, let's do one more, and then we can shift over to review. All right, next up, find the general solution for this differential equation. We know it's a differential equation anytime there's a derivative variable involved. And then we'll find a particular solution, just like the steps that we did. We're going to cross multiply, separate the variables, to take the antiderivative. And then it says, then find a particular solution given the order pair. So a general solution is where you're leaving a C in your answer. A particular solution is where you're going one step further and they're giving you a specific order pair, which means that we can pinpoint C to be a specific number. But let's worry about the general solution first. My first step is I'm going to rewrite that y prime. The y prime can be written in a more detailed way. So anytime you see y prime, you can always rewrite it as dy over dx. It's more descriptive that way. And that way we can also make sure that our dy and dx's are going to line up nicely. So anytime you see y prime, rewrite it in a more formal way, in a more descriptive way. Okay, our next goal is we would like to get two fractions to be equaling each other so we can cross multiply, so that we can kind of work towards getting that dy and dx's lined up. So I'm going to force both sides to show me individual fractions so I can have an a over b equals c over d, because then I can cross multiply. And cross multiplying just makes things cleaner because all my denominators will be moved, and I can hopefully get my dy and dx's lined up where I want them to be. Okay, so I want to keep reminding us that cross multiplying doesn't quite get us to where we need to be for our full separation, but it will take care of that dy dx's, getting them in their right spots. So first thing you want to observe is make sure your dy dx's are in place, and they are. And the next thing is asking, are the variables nicely separated? Are the y's together on the left? Are the x's together on the right? We do, right? So there's no need to move anything else. This is already naturally going to have full separation. But I like to do one thing is eventually the y has to be by itself on the left, and the 3 has to come over eventually. You don't have to move it now, but for me, I just like to kind of clean things up as I go. Just means less work down the road. So I just like to, if I see anything that I can move away from the left side, I'm going to do it. But technically, you don't have to. You can wait till the end. So there's some room for different steps if you like. So I like to have that left side as bare and minimal as possible, if I can help it. So still full separation. And now everything is ready. We're still at the derivative level, but we've gotten everything lined up nicely. So now I'll take the integral of both sides. Now both left and right are showing me power rule. So we're just going to go through power rule, y squared over 2. X squared over 2. Let's see. Questions so far? Okay. We're basically at the function level. The rest is cleanup. So cleanup just means trying to work on getting that left side even with even less things. So we want to get all the way down to y if we can do it. So I see there's a y squared over 2. There's a denominator of 2. If I can multiply everything through by positive 2 or 2 in the numerator, I should be able to clean up that 2 in the denominator under y squared. So here the 2's cancel out. I'm left with still negative 2/3 x squared plus c. So I think this is good enough to call this a general solution, because we have the C is still unresolved. We can do plus or minus, but this is okay. We can leave this and call this the general solution. Now we're going to move to the particular solution. So particular solution just means figuring out what the C value is, and then we can also go one step further and solve for Y. You can solve for C anytime you want. You can either solve for C at the end or at the beginning. I typically look at the equation and see, okay, when is the equation going to be at its least complicated? So I would like to solve for C at this point, because if I wait longer, I got to deal with the square root. It just feels a little bit messier. So I'm going to just find my C value at this point, because this does feel like a relatively simplified or simple equation without the square root. I'm going to go ahead and plug in. Okay, now having said that, you can solve for C at any moment in time. You can wait to the very end. You can wait a little bit longer. It just, wherever you want, ultimately, you can decide where you want to solve for C. All right, I'm going to plug -2 in for Y, 1 in for X. Add 2/3 to both sides. That's really 12/3 plus 2/3, which is 14/3. Now, once you solve for C, we're going to plug in back into the equation. But make sure you plug into the equation where you started making your substitution. So wherever you make your substitution for your for your X and Y is where you want to be plugging your C value back into. So now I have my C value. I'm going to now focus on trying to get that, Y by itself. So I want to get that Y by itself, I got to do square root. But if I do the square root, what's going to happen? If I take the square root of both sides of the equation, what else is going to show up? Plus or minus. So we'll do plus or minus square root. And then once you have that Y by itself, I don't really care what you do with the right side. You don't have to do any cleanup. You can leave your answer as messy as you like, as long as that Y is by itself. Now, technically, these are two separate functions, right? The plus or minus are going to be basically overlapping each other. They're not going to, these are two separate functions, which means that we only want to choose the solution that is passing through that point. Okay. And the easy way to tell is you look at the Y value. Whatever the sign of the Y value is the sign that you want to produce that Y value. We want to be able to plug in an X value and get a negative number in return. The only way we can get a negative number in return is if there's negative sitting outside the square root. So because the Y value is -2, we want to keep the negative square root, because that's the only function that's going to return you that order pair. So if you're ever having to choose between a plus or minus as your final solution, look at the Y value of your original equation. That's going to help guide what sign you want to keep. Okay, we'll pick this up tomorrow. We're just going to continue working through this. But let's go to our test review. Page 2. I don't know if we finished page 2, so let's pick up where we left off. Okay, bottom of the page here. Find all the values of x where the graph has a point of inflection. We know that if we're looking at the first derivative graph, points of inflection are basically the peaks and valleys. So let's just create a slope, a concavity sine line based off of G prime. So again, my endpoints is between -5 and 4. And I'm just picking out the hills and valleys of my f prime. Sorry, of my g prime. This is my f of t, but this is my g prime graph. So -3, 1, and 2. We look at the slopes of the g prime graph. We start off with a positive slope, then we convert to a negative slope. It's going to keep alternating, right? But a second derivative that's going to represent concave up and down. So it looks like how many points of inflections are we going to have? 3, yeah. Each of these have a change in signs that indicates that's a point of inflection. Okay, let's do another derivative graph. So page 3. Okay, anytime you see this relationship, a g and f, where there's an integral on the f, you know that there's a staggered derivative relationship between the two functions. If this is f, then we can also know this is really g prime. But let's build all the relationships that we need in front of us, right? So if we know that, well, g of x is just the area under my f of x graph or f of t graph, I know therefore g prime must be the derivative of this mess, which second theorem will just tell us a bunch of stuff cancels out and the x gets plugged in for f. So I know that my g prime is just at the f level. If I go down another level, I can make both go down the derivative. So g prime becomes g double prime, which means f will become what? F prime. So I'm just doing this at the beginning because I know that my problems are eventually going to reference g, g prime, and g double prime. So these will be our kind of our guide for building that relationship. Now I know I have to involve areas eventually. So I'm going to go ahead and find the areas of each of them and know that positive is above the x-axis and negative is below the x-axis. So, but I think this is worth doing, even though it may seem obvious. Highlight your regions between the graph and the x-axis, because if you don't, you may get tempted to build areas that's not part of our diagram. So go ahead and shade in what you see between the graph and the x-axis. Okay, let's go ahead and find the areas of each of these regions, and that we can just easily reference. So first is a triangle below the x-axis. So we know that's going to be negative. So 1/2 base times height, I get -1 here. This is a semicircle, which I can split up into two parts. 1/2 pi r squared. My radius is going to be 2. So this is this whole thing ends up being negative 2 pi, which I can break it down into negative pi and negative pi. Because these are both below the x-axis. And I'll go ahead and split up this triangle into 2 parts here. 1/2 base times height. This is going to be an area of 2. This is also positive 2. Just want to have everything in front of me so I can just get that out of the way. Okay, so find g of 2. So g of 2, we look at the definition. Definition says my upper bound is where the x goes. So from -2 to 2, -2 to 2, what does this end up giving us? Well, first off, are the bounds in order? Yes, so that's good. That means there's no need to adjust the bounds. They're already going from left to right. So from -2 to 2, we add up those regions there. So that's just -2 pi. Okay, find g of -4. Follow the definition. Plug in that upper bound with -4. What about these bounds? Yeah, they are out of order, so it is worth the time to rearrange it so that we can read from left to right. But just remember to pull a negative out in front. Okay, so from -4 to -2, I have -1 minus 2 pi. I'm sorry, -4 to -2. My bad. -4, -2 is just here. That's going to be -1, but I adjusted with a negative outside as well. So negative over -1 is going to be a positive one. Next up, g of 6. G of 6 definition from -2 to 6. So -2 to 6, we're going to add up all these numbers. These are in order. The bounds are in order, so no need to change the bounds. So -2 pi plus, wait, is that right? -2 to 6. Yeah, -2 pi plus 4. All right, next up, find g prime of 4. So g prime of 4, we have a different relationship there between g and f there. We know g prime of 4 is equal to f of 4. And what's f of 4? Yeah, that's just, now we're looking at simply the order pair of the graph, right? G prime of -2, we know g prime of -2 is f of -2. And what's f of -2? 0. All right, another change in relationship, g double prime of -5. So g double prime of 5 is f prime of 5. F prime of 5, here's 5. We're asking for the what of this graph? Slope. Yeah, so pick 2 points that are easy to identify on this line and just do rise over run down to over 2. Slope of -1. So you're either involving the area, involving the order pair, or involving the slope. All right, next up. Find for what value of x is g increasing. So increasing, we're talking about, we're looking at, this is basically the f graph, but we know this f is really g prime. So we're basically looking at g prime. So let's label our derivative graph accordingly. Above is positive slope, below is negative slope. On the x-axis, slope 0. So here's my g prime sign line. Pick out your x-intercepts. -2, 2. Look at the arrows that you see here. We start off below. We still keep below the x-axis and then above. So we have negative, negative, positive. So the sign lines can help us answer our question. Where's our g graph increasing? G graph is increasing from 2 to 6. Because my g prime, which is my f graph, is greater than 0. Where's my g decreasing in these two intervals? I'm going to split them up. Next up, find all points of all values of points of inflection. So we have to create our second derivative sign line. We know second derivative sign line comes from our peaks and valleys. So I have a relative max, relative min, relative max. So these all can go onto my g double prime sign line. There, look at the slopes. I start off with a positive slope, then negative slope, then positive slope, then negative slope. And then we know the slope, we know the plus and minus on the g double prime is related to concavity. And so these are all points of inflections, right? We have change in signs for all of them. Next up, find the absolute extrema. So what is this? They're asking us to apply what? EVT. So EVT says find your endpoints and critical points. Don't pull them from G double prime. You're only pulling what you need from G prime. Okay, when you're doing EVT, just pull them from G prime. Okay, so out of these values, which points do we have to worry about to test? Well, look at the signs though. Do we need to worry about -2? I mean, we can. Okay, so it's not wrong if you want to test all the points, but if you don't see a change in signs, you don't have to test it, because if the graph is decreasing and continues to decrease, it won't be it can't end up being a max or min. So just make sure you test your endpoints and your relative max or min. So just worry about -4, -6, and 2. Again, it's not wrong if you tested more points, but we only have to worry about these 3. So they go back into your definition for G. So we want to find G of -4. We want to find G of 2. And we want to find G of 6. We may already have some of these values that we gathered from before. I think we already have G of 4. Sorry, G of 2, G of -4, and G of 6. So we already have all these values. So that's great. We can reuse them and use them to help us find our values. So G of -4 is 1. G of 2 is negative 2 pi, and g of 6 is negative 2 pi plus 4. Okay, if you don't know which one is your higher or lower y values, you can plug in the calculator. But this is 1. We know pi is around like 3-ish. So this is around like negative 6. And this is around like negative 2. So if you're comparing between 1, negative 6, and negative 2, you know negative 6 will be the lowest absolute min, and 1 will be your absolute max. And just give me the y values for EV2. Okay, let's do a Riemann sums problem. So let's go to page 4 is another derivative graph. Let's go to page 5. Okay, the table shows the speed of a sprinter at the time interval in seconds in 200-meter race. So 0 seconds. When time t equals 0 initially, the sprinter is going to be going at 5 meters per second. He's going to increase his velocity all the way up to 9, and then he's going to slow down a bit near the end of the race. Okay. Anytime you're dealing with integral, your units will change. Okay, and that is something I know right now it doesn't. I think with particle motion, students tend to not have that much issue, but whenever you do your integral notation, there's basically area involved, right? So whenever you do area of something, your units will always change, right? You can't stay meters. And so an easy way to make sure that you have the correct units is you're always multiplying the units here. So in this case, what's meters per second times second? Meters. So just always do that, okay? Always do that. And then if you know what the units are, it's a lot easier to interpret what the problem is doing. I know right now it doesn't seem like a big deal because it seems obvious I think we're pretty comfortable with particle motion, but if there's rates involved that we're going to see later as we do more review over the course of the week, that a lot of students tend to forget that the units change and they start talking about something in this unit, which is not true. Okay, so anytime you do a calculus procedure, your units will change. If you do a derivative, your units changes. Your integral process, your units also change. So everything here is going to be in terms of meters, right? Okay. We have a formula for trapezoid, but I introduced a way that we can avoid having to go through a trapezoid formula. And the idea is that trapezoids is the same as doing a left rectangle sum plus a right rectangle sum, and then just finding the average of those two. So adding the two of them up and divided by 2. So you can either go through this area formula, or you can go through doing left and right. So let me see. Okay, just for time's purposes here, let's do 3 trapezoids instead. So again, 3 trapezoids. You can use this formula if you like, but I think for most, if we just know, left rectangle, right rectangle, and then just finding the average of 2 of them. So I'm going to go through this process of doing left and right separately and then adding them together. So left is just width times height. We want to make sure we have our subintervals identified. So we're going from 0 to 20, and we're spacing each of the subintervals, and every subinterval is going to have a repeated use of the first order pair of the order pair before it. So we'll go, and you always want to go from middle to middle. Don't start at the lines there, that throws you off. So go from middle to middle. So I have, if I want to do 3 subintervals, then I need each subinterval to span across the same number of order pairs. So each of them will span across 3 order pairs. And if I subtract the x values or my t values, I get my width. So 5 minus 0 is 5. 11 minus 5 is 6. And 20 minus 11 is 9. So these numbers are the width. And then the bottom number is where you pull the height. So my left rectangle is going to be 5 times 5. Middle rectangle, width of 6, height of 7. And last rectangle, width of 9, height of 9. Okay, so that's my left rectangle. I'm doing trapezoids, but I know that I just have to find my left and right separately and then find the average. Let's do the right. And also 3 rectangles. So the width will stay the same, 5, 6, and 9. But your height will change. Your trapezoid is just averaging these two together. And then your units is meters. So I think we were able to answer 2 and 3 because they're just 148 and 156.5. Okay, we'll pick this up tomorrow. And tomorrow we'll continue with notes, and then we'll just use 20 minutes to continue working through this review.
Can we keep the calendars?
Yeah, calendars for you.
Yeah. Yeah, you are.
That's the type of slide.
See you tomorrow.
It's crazy.
Thank you, but he said he's also like different though, which is just like choosing the correct answer and pay. Yeah. Oh, what did it was Harry?
That's all. Okay, sure, yeah. What's that?
I should send that email. I thought you were talking about
Nice guys.
You're putting the computer back in. I'm keeping it off, I can pull it out.
No, I don't answer.
I thought this guy's not very cool.
I didn't have this, I really wanted to stay and see how the house would be.
You just, you do this. Yeah, well, I figured it out now. You do right plus left.
Yeah, I figured that.
Right, no,
I forgot how to do it. I forgot how to do all the rings, like all those came back to me.
oh, while you're.
No, while we were doing it all. And we did tests like Thursday. On privilege, like that, so.
This last I want to see where. I want to see where.
Oh. Good. Yeah. What's called? I don't think the word. You don't think the word can planet.
Morning. Morning.
Why? I already have. Yeah. I was not there, but I thought you don't have the original Saturday vacation. I tried. Okay. Want to eat pizza around and you want to bring it's like really chill. We'll see, maybe it's always such different. Yeah. Okay. Here, you're with me. No. Definitely access the. I know you're going to. But I like that I could like. I said that increase. Yeah. I like those kinds.
No.
Everyone else. You.
No.
I'm shocked. Oh, Ellie, what's your first time?
I did not hit one yesterday. Good. It's a good idea. I know, you talked me out of it. Actually, I did like twice today, so. We're at the gym, we're at the gym, I told him, saw him, he's like, dude, why are you in Mike? I'm like, because I need to. Because I didn't hit it Sunday, and you didn't hit legs on a Monday. I'm like, oh, okay, guy. And then I legit ordered the squat rack, did 135, I'm like, nope, not today. No, I was like, I swatted the 10 reps, and I'm like, good point. What? Yeah. Warming up, bro. I didn't have warm up. Brother not warm up anymore. Yeah, we start up 2:25 or like, yeah. Okay. That's a good thing out. Yeah, it's just like that. Well, it's like, what the fuck is the warm up?
Maybe whatever the quiz is. Oh, my God. That's fine. It's like.